Hi everyone, this is Prakash, and this is part of the Learning Quantum Core for Application. This is a 6 session event. This is the first session, and look forward to working with the Silicon Valley Quantum Computing and emerging OTF, which have come together to deliver this. What I have now is the session detail for the session 1. This is a course of 6 sessions. Session 1 will cover the so overall of the 6 session, first session is on this fundamental and history of quantum. The second will cover the math or some of the fundamental, and the third the math behind, second the math behind, and the third something on the circuits and all, and polymetrics matrices. Fourth one will be on the algorithm, and then fifth one and sixth one will be advanced topics depending on the interest in the team related to both circuits and uh, what you call the quantum circuits, as well as on the algorithms and applications of sensing and other material. So with that, I will just ensure to see that the recording is going on before I flip. Yep, the recording is going on. Thank you. And I will move on to the viewing the session here. So we go on to the session 1. Session 1 covers the so first thing is thanks for the sponsorship by the team, which is Emerging OTF, as well as the Silicon Valley Quantum Computing Meetup Group. We'll be covering the details, as I said. So QML Meetup Group and UTF both have decided to invite people to complete the what you call the course. This is a certification course for 6 weeks, and Dr. Tupash and myself, Prakash, we are trying to ensure that you will be able to learn on the quantum qubits, which is the logical we can take equivalent of the binary bits in quantum, and then correspondingly we'll have the computing and the infrastructure related work to superposition, as well as on the acceleration which the quantum computer brings in. It will also cover some of the communication aspects, and those are related to the entanglement, and which is what is important from communication point of view. It's related to time, space, and obviously this communication has channels, and the channels could be Nyquist, which is multi-level, which is the quantum, more likely to be for quantum because you have multiple channels. And then you have what do you call the Shannon's, which is the generally used in the binary and information theory. That apart, we will be focused on the algorithm, and the algorithm will include the what you call the quantum algorithms, as well as the quantum circuits through which it is implemented, and applications can be of any vertical that can be applied on this. To just remind you that there are two. One is the adiabatic quantum, other is the circuit quantum, so gate quantum. So we will be mostly be focused on gate quantum. Adiabatic quantum, maybe in the end session we'll look at it, but that's more related to thermodynamics and heat theory and entropy and energy, etc. And their equivalency in what you call decoherence is the equivalence of that for the adiabatic process in circuit logic. Then we'll also cover sensing portion. Sensing obviously is for measurement, and once you measure, the states collapse, and that's the reason you need to be right before. Once you have completed all the operation, then only you try to measure at the end, so that it collapses to the desired state which you are looking for. And this is a probabilistic model, and one thing is accuracy and precisions are important, and how we ensure that there is a fidelity of the repeated process to get that is another aspect. So there are some issues with error correction and all that is required to be able to deliver that. Besides the in the sensing P and T, that is the position, navigation, and timing, which are accurate requirement, and accuracy of timing is very important because they are in the microsecond range when you do the millions of computation. That said, I will move on to the second topic here, and that is comparison between classical and quantum, which is the major portion here. Then we'll cover the historical of the 20th and 21st as to what quantum technology, science and technology brought in, some of the industry application and landscape of the quantum stack, and the particles and wave differentiation and superposition and entanglement. And typical quantum characteristics, we'll look at what characteristics of quantum needs to be measured to interpret the results. If you try to measure directly, the state will collapse, and therefore you need to measure the characteristics associated with quantum uh, processing or quantum phenomena. Then we'll talk about relativity and communication, and finally the glossary, and then the recommended reading we available with us in the link. So let me move on to the slide, which is relating comparison between the classical and quantum computing. Here the subject is, if we talk about the representation of information, and we do it through the 0 and 1 bit, and that's a voltage level being 0 and 1. This is based on the semiconductor switching, or even for that matter even mechanical switching you can use, but mainly it is based on electron semiconductor, where even there is a Fermi level of energy, and if you are able to cross that Fermi level by applying voltage, then you are able to get the amplification necessary to distinguish between 0 and the 1 bits, which is called as bits. Are usually earlier attempts were made for decimal multi-level computing, but for reliability reason they stuck to the binary, and which is very very reliable. Quantum computing is of course multi-level, but it is probabilistic. So if we talk of there will be a qubit corresponding to a bit, and the qubit has a state of 0 or 1, which is referred as spin up and spin down in terms of electron spins. And so bar with a 0 and a greater than is the ket 0. Bar with a 1 with greater than is a ket 1. So the linear combination of algebraic, in this case we are showing a ket 0 plus b ket 1, that is a qubit, and that is described as usually ket psi. Psi is the symbol we use for generally, and that psi, ket psi is the sum of the linear combination of a ket 0 plus b ket 1, called the qubit. This is the one qubit. If you have two qubit, you will have four terms, so on and so forth. If you have three qubit, then 2 to the power 3, then there will be eight such what you call the uh, complex uh, terms along with the corresponding states. So superposition is used here, and that is the basis for our states here. So ket 0, ket 1 are spin up, spin down. You can have similarly. This is the standard basis for measurement, we call it. You will learn about it as we go. So operation principle, classical is based on Boolean algebra, logic as we call it, and or not, NAND, etc. Whereas in the case of operation principle in the quantum is either superposition, entanglement, or interference. So it could be constructive, destructive interference, or it could be interference because of the noise, etc. So logic gates are usually non-reversible. So example, AND gate, if I say 0 0 is 0, 0 1 is 0, 1 0 is 0, but 1 1 is 1. So if I have output 0, then I don't know whether it was because of 0 0 0 1 or 1 0. So it is not reversible. So that is about the logic gates being reversible, not reversible, whereas the classical logic gate. Whereas if you talk about binary, we talk about quantum qubit gates, then they are unitary. Unitary in the sense that they always will be normalized to one state, normalized to one. Like example, if a ket 0 plus b ket 1 is there, the normalization will be a square plus b square. So a upon a square plus b square. A square plus b square is a probability which is equal to 1. These are just the density terms. So a upon under root of a square, which is equal to a in this case, and b. So the a square plus b square are the probability, in fact. So that a square plus b square is equal to 1, and these are just density terms. Same way, the unitary aspect of that is shown, normalized. And reversible means if you have two inputs, there will be two outputs, and whatever you input, you will get whatever output you get. If you give the same uh, output, then you can get the corresponding input. So essentially, they are reversible. Example, the greatest example is discrete Fourier transform, where if you give time to uh, frequency domain, whatever time base sequence you give, you get a corresponding frequency, and if you give the corresponding frequency inputs, you will be able to get a time basis samples. So that's a reversibility. Robustness, of course, when we talk about say 100 degrees centigrade, let's say, they are in the order of 373 degree Kelvin, because 273 is the minus. So we are saying that they are robust and they can even work up to 400 degree Kelvins, whereas these, which are um, quantum, they generally, because they are susceptible to noise and thermal noise especially, and the low thermal noise occurs either in vacuum or at the low temperature. So both vacuum and low temperature are the need for the making a super subatomic particle transformations, which is what quantum computer does. Then measurement, you can copy and determine, like in buffer we copy and we do a sorting, etc. So that's the measurement in classical computing is possible because you can copy and paste, and it is deterministic, whereas in case of quantum it is non-deterministic. That means what, it is not deterministic, it is probabilistic. And then when you try to clone, they collapse, and therefore you can't clone. So the way to some of the alternate ways to be able to convey is through the what you call the linear combination thereof, and then making sure that a copy of that is retained, whereas when you measure on one side, the other side, a copy of it is rather not the copy but the teleported version is available, and from where we can determine. So it's possible, but it's not copying true sense. It is just a teleporting, we call it. So that will look under the entanglement process, etc. Hardware-wise, diode, transistor, binary gates, and levels of integration of IC could be medium, large, or very large. You can use with the binary system, and millions and billions of gates are put on a CPU, etc. If you look at the very large scale, application-specific integrated circuit, or even the advanced CPUs with multi-core and all. Whereas in quantum, we are still in the NISQ era. It's called noisy intermediate scale quantum. NISQ, and in the NISQ era, what happens is you do have uh, what you call bits, qubits, number of qubits attainable are the order of only hundreds to maybe thousands at the best. In the superconducting quantum, or what we call as circuit-based quantum, in the adiabatic, you still can reach around 4 to 5,000 at this stage, but they are not very scalable. For scalability, we need fault tolerant, and that's what will be the next generation and future for the quantum computing. These are based on various physical implementation, like Josephson junction one uses in the microwave, and those frequency ranges in the millimeter waves and so on and so forth. You can uh, really use this on a, of course, junction means you will have some aluminum and uh, silicon or aluminum, germanium, etc., whereby the semiconductor and the conductor semiconductor substrate is coated with aluminum, etc., and then thereby you are able to puncture through the tunnel instead of avalanche where you go over the what you call the hump. Here you drill a tunnel in based on the electron, and you are able to get the similar effect, but the larger effect in terms of superposition and entanglement. Then information size, we talked about 1 bit, 8-bit register, 16-bit register, 64 and 128, which are the normal for classical. But in the case of quantum, we still have 5 to 30 qubits is what is really currently it's used. And but their logic is different. They are not something like carry forward and all that. They may have some different action like swapping the qubits, or maybe applying some gate logic like Hadamard, or maybe some uh, Tifoli or some Clifford. So there are different gates terminology which you will come across in the quantum computing, and you can do a hybrid combining the two. So that was about the uh, what you call the classical to quantum computing comparison. Let's move on to the uh, here we are looking at. I hope you are able to see the. I think I will go stop sharing and then reshare because I don't see uh, uh, the screen that I needed to see. So let me go to the share and reshare the screen so that you are on the right share of the screen. Okay, so let's look at the share now. Okay, sorry. So let me see whether. Okay, I see. So when I spoke about the mm, sharing, I did not see uh, what I was talking about. In from the beginning, looks like there was some problem here. It's a challenge trying to fix this anyway. Let me just share and start with again. So uh, when we were talking about the sharing, I hope you were able to. I'm not going to go through it again, but you see the subject and the classical versus quantum, and this is what I had spoken about previously: operation principle, logic, and robustness, and measurement, hardware information, and all that. Same way, if I had missed the previous slide, I would just want to make sure that I show that also before I move, because otherwise you would have lost all the meaning of what I said. So let me share, sorry, let me go to the uh, compute and make sure that you saw this portion which I was describing previously. So here is my, I'm puzzled by this, but nevertheless we have to do our proper presentation. So hopefully, if you have not seen this, this was the picture over which I was giving you the fundamental about the quantum qubits, the infrastructure, the communication, the algorithms and the applications, and about the sensing. So this was the present. This should have been shown to you in the first when I started. I had only seen the table being there. So unfortunately, that's what it is. So let me just move on to make sure that every time I do a click on the slide, I can move it out. Yeah, you can see this. Oh, thank you. So looks like you are now able to see. I hope I'll just click on this to keep continuing. So the next one, we are going to talk about the history of uh, quantum, and this basically is to make sure that you have the core, which is the quantum core. The learning quantum uh, core. That is what we have described this courses. So quantum at the core involves the quantum qubit and the stack which is able to generate that qubit, and the physical layer is either a photon or electron or something of that kind, which is the physical infrastructure which is used for computational for the superposition through superposition and entanglement. So communication and computation work through superposition and entanglement, and the noise has to be reduced. That's the focus for getting the higher fidelity as well as for the parallel, as well as computing and multiple nodes. If you like, we talk about the quantum internet. The quantum internet may need a optical, may need a what you call free space if it is using satellite for the communication. So those are the things which are important. And when we tie these together in the applications, we'll know more about it. Sensing is another piece which requires measurement, as I mentioned earlier. And the gates are there, which are the quantum gates, and not the typical logic gates, which are not reversible nor unitary, whereas the quantum gates are, all of them are reversible and unitary. Whereas in classical computing, not gate may be reversible, but not every gate. So that's one. And then there is one more XOR, or control XOR, which is equal to C naught. We call it control naught. So that those are the gates we'll talk about in session 3 or 4. So simulation, like your twin, digital twin, we talk about, that is the which can be done for any application or any domain using the quantum through the speed up process, which is much faster. Coming to quantum, it has been a century old phenomena, as you know. And we have in 1930s, when a bunch of mathematicians, physicians and some of the chemists and all came together, and they actually set the stage for defining quantum. There were arguments, there were debates, there were papers, and many of them are Nobel laureates, especially those who are from Europe. And the biggest one is Einstein, everybody knows, and he was the one who proposed the photoelectric effect in 1921. And prior to him, the more important person at that time was the uh, Planck, who defined the quanta theory in 1918. That is the particle theory, particle and wave. And the wave was what you call Schrodinger's proposition. uh, but integration, and Bose was one of those, Satyendra Bose, who assisted Einstein through correspondence from Calcutta, and he was one of the contributors to the relativity theory. And Heisenberg was the one who who brought in the uncertainty principle. When you measure quantum phenomena, you can not measure simultaneously both accurately the space and the time aspect of it. So that's one thing. So if you have multiple parameters associated with quantum phenomena, you cannot measure them together. There will be some uh, uh, kind of a relative, some kind of a accuracy loss, and that is what, because they will not be in the same time. There will be, it cannot be simultaneous to the exact percent, and therefore there will be some minimum inaccuracies, so that can be accounted for. So the basically all of these put together several of the theories, and ultimately the quantum grew. And Dirac was one of those mathematicians who was able to bridge the gap between the wave theory and the particle theory, and he brought it together in 30s. And then while these people described everything properly, in the 40s it was the Turing who advanced the architecture of classical computing, as we call it, as using endless tape as a memory. And that's what led to the furtherance of the classical computing. And classical computing also had some communication aspect, like we talk about the Shannon's theory and the Nyquist. Nyquist formula was more to do with the multi-level computing, whereas Shannon was more focused on the binary aspect of it, and he was the father of what you call the uh, information theory, where if it rains in Seattle, it's not in news, but if it rains in some desert, it's a news. So the probabilistic aspect is uh, the probability it will rain in Seattle is much higher than, so it is not in news. Whereas probability that it is raining in desert is in news, so it has got a higher probability. So that probabilistic approach was brought by Shannon in the 40s, 48, and he was also one of those IEEE awardees for ACM. He is something like in his name there is a ACM award and IEEE award being given to folks in US. He was one of those primary guys who drew the information theory in the probabilistic approach and the estimation of the channel against the noise. Example, SNR is the signal to noise ratio. So B is the bandwidth, the capacity based on the log of log to the base 2 of the 1 plus SNR. That's what his formula was. Whereas Nyquist was more focused on the uh, twice the bandwidth of log to base 2 of the levels of L. So more the levels, more the capacity. That's the assumption, but that's not infinity. That is limited by your signal to noise ratio per channel as per Shannon. So both of these will be used in the qubit communication. And we'll move on to Richard Feynman, who was credited with uh, several people call him the father of quantum because uh, he was a physicist and he was at Caltech. He was born in 1918 during the time these people actually, he was young those days and he literally uh, put together all the physics approach of how electron when you draw it in terms of line and how it travels and how it emits photon and then it recombines the photon. So all this theory which Richard Feynman has written are very popular among the quantum mechanics folks, and he was in Caltech and he predicted that quantum phenomena can use speeding up even better than the classical. That was his. And then of last few 10 to 15 years, 2010 we had the first quantum computer rigged out here in the valley, Silicon Valley, at what you call the one of these government organizations here. And then uh, that's where it became that evident that you can use quantum computing, and that's how it came to be the beginning of quantum era. And then D-Wave and INQ, some of those companies which were in the adiabatic, D-Wave specifically, which was in the adiabatic process of creating quantum computers, took off. Then there were other Rigetti, and then there are many other in the last decade or so. Several companies have spawned, and some of them survived, some of them moved on to adjacencies where they can exploit the investment made in them. But of late, after the uh, award Nobel Prize to John Allen and Anton, who experimented the Bell state. Bell state is John Bell predicted in '65 that there is no spooky spooky action at the remote as they call it as EPR. Einstein, Polowski, and Rosen had doubted on the quantum theory of being what you call complete. They suggested some hidden variable, so that hidden variable all were debunked by John Bell through his theory of probabilities calculation, and finally it was also proved by John Allen and Anton. And I think all these are living folks. Anton is currently the part of, I think. He's in the one of those who is in the Paris, and the Pascal Computing got 100 million last year, and they are one of the primary drivers in what you call quantum subatomic particle, where uh, they have focus on the uh, what you call the way of building without they call it as neutral particle, so neither it should be a positive or negative any so some of the terminologies you will come across like anion, boson, and so on and so forth. So but for our practical purpose, electron is good enough to represent, and maybe photon, these two should suffice to carry the circuit based quantum, which is what we are focusing on. Moving on to the next slide, hopefully it shows up. Yeah, thank you. So I can see that the industrial applications are many possible, and government laboratories, obviously they have the funds, they got the funds to innovate, and since the competition is global, several of the government are trying to build their um, expertise in quantum computing, and therefore the every country has its own the reasons are very evident because quantum there is a threat of security if quantum is developed. In that case, they can break the keys, and therefore, to protect against the keys, people have to learn how to protect the keys. So there were National Institute of Standard Technology in NIST in USA has put down the what you call algorithms, asked our all the hackers and everybody to put down how do you break or how do you not break uh, various algorithms like elliptic algorithms, where the most uh, mm, popular now. Instead of that, lattice algorithm is becoming more of a standard, and we can expect that implementation of post quantum cryptography, what they call it, sometimes in a year, in at least in US, and the whole of the world will follow. We call it as Y2Q, something like a Y2K in 2000s, when the breakout of various devices were expected, and same way Y2Q is likely to be projected for next year. And when government organization all through every nation will one by one follow that. So there is, even though there is no quantum, but you can crack. If you have a 7 year records of finance, you can, if you save it, you can crack it after 7 years. So all these past RSA algorithms, our current RSA algorithm will become obsolete. That is when you expect that 756 or something of order of 1024 key need to be there, and they are will be based on lattice algorithm. So all your SSH and all this will be uh, updated with the newer versions, and so you can expect a lot of this due to the government laboratories and all the government organization to secure. So that itself is a big application, even though it is not quantum specific, but to protect from quantum keys is and key distribution, etc., is going to be very important. And key distribution part also comes along with communication. We'll talk about it. Pharma, we have just gone through the pandemic and COVID-19, and everybody understands the power of virus. And to overcome that, you need some kind of a understanding of the first thing is genomics, that is the DNA, etc. Genomics, 2003 was when it took almost 13 years to decode the human genome, and which is 97% of all human beings have similar genes except 3% variations and mutations, etc. But even to do that, currently there are a lot of models available, and so the amount of effort required is more becoming computational. How do you compute the 3% difference to be able to identify the various uh, anomalies or mutations, and that may or may not be responsible for a certain kind of what you call uh, certain kind of variation in the human capability, and that is either you may have some anomaly, and that may be detected using the computational methodology by deciphering the DNA, RNA. RNA is nothing but messaging across the genes and all that. So, genomic, proteomics, all these are part of this pharma, where you can do drug discovery to enhance, protect, etc. And they are all based on various digital format, and it's called sequential. So when you have a sequence, they call it as mapping, sequence mapping. So when you do a sequence mapping, you can also do it to compress it using binary. So there are there's something called binary classes and FASTQ, which includes some kind of metadata. So you apply this, you compress, and then apply it in the mapping the alignment, and then you can do the decompression on the binary maps called BAMs, alignment maps. So BAMs can be input and BAMs can be output. So you can decompress them, you can compress them, and then you can apply all the markings and sorting and duplication. And finally, you do the variant calling, that is how much of variations are there, and you can collect all those information. So this is a kind of a bio IT system, which is on the S3. You can this available in public, and you can go through the guide to understand how we can apply. Maybe this is still not applying application of quantum to it, but one can use it. So pharma industry has a great in drug discovery, and then various what you call the MRIs and all, capturing the detail and all that. So this is one of very, very health area is very important where we can use manufacturing. All of us know about the chemical industry, the fertilizers, and so on and so forth, and also on the side of like designing a aeroplane, aerodynamics and all that. So both mechanical, chemical, those which are industrial manufacturers, they require a lot of processing and using what you call the quantum computing. Also, some of the robotics and all, arms movement, and same way with satellite launching precisely, like mission to the moon, mission to the Mars, mission to the sun, etc. All those can be applying the computational capability, and that is one where we can use this. And then transport is a standard supply chain problem. Yeah, what you call non-polynomic NP hard or NP hard problems like traveling salesmen are very popular, and this is a very key for the supply chain. And how do you optimize? So optimization aspects, etc. Finance, everybody understands that the Wall Street or the Dalal Street or whatever your exchanges are, where you take a decision to invest or withdraw, or so bull and what to call the bear markets, when you play with the money. And if you in the especially the big firms gain a lot, and also government because of fluctuation in the currencies and all. So this is fintech is another area where a lot of applications are there applicable, including the cryptos, which is part of government as well as the communication. And so you will find that security is important. So this finance is also equally important in this case. So what we want to say is that there are many applications, including the alternate energy like solar, agriculture, drone, and soil testing. And those are the various other applications which are not mentioned here. But important here is that you have several applications that are possible, and industry application using or leveraging quantum, both the computer communication and sensing, like weather predictions and all. Those are some of the fantastic applications where quantum is applicable. Quantum can be used. Quantum theory can be used as well as the computational mechanism. Now I'll move on to the next one, which is learning landscape of the quantum stack. So normally our computational stacks, we have seen the various stacks, including the open source LAMP stack and the computer science stacks, and also very similar to what you have the TCP IP stack for communications or for the OSI stack. Similarly, this is a quantum stack. This is a hybrid stack because you have quantum hardware, which is the subatomic particle manipulation through the swapping and the pulses and through the time sequencing and all that, clocks and all that. And then you have operating system. The operating system, standard operating system won't be able to handle the quantum hardware. So you have to bring the what you call quantum primitives, and that quantum primitives can be written in quantum language like quasm, like quantum assembly language, or some other which can be interpreted. And those are the ones which are relevant to us. The classical language, as I mentioned, classical language and classical compiler, we need to be um, what you call altered or modified or updated to include the quantum premiums which operate on the along with the operating system on the control circuitry, which will be quantum circuitry on the subatomic particle. And obviously this is a framework which will include both the classical CPUs and the GPUs and the QPUs of this quantum world. So then you have to have algorithms which drive them, and the application that you leverage them in the verticals. So you can see the level of abstraction goes from low to high, and all of these are based on the standard qubit, which is the spin up, spin down standard basis implementation. Or if you have a linear combination example here, ket 0 plus ket 1 divided by root 2, this is the one usually called as what do you call ket plus and ket minus. So there are various standard symbols used: ket 0, ket 1, ket plus, ket minus, ket I, ket minus I. Those are depending on the directions, and these are standards, and we will know about the standard. But standard basis is always the ket 0 and ket 1, and that's important to note. So this is about the stack. Now we move on to the next one, which is particle and wave theory. You are aware of the superposition and entanglement. It's important to note that we should be able to do superposition. If you, example, if you have two waves and this is wave function one, wave function two, the two can be additive and two can be destructive also because they are in the opposite direction. So you can have a constructive or a destructive uh, superpositions, and that allows us to eliminate some of the possible solutions or enhance some of the possible solutions. So therefore, it speeds up. Example, using the Fourier transform or a discrete Fourier transform or quantum Fourier transform, what we call unitary. Then you have got entanglement. You have got the phase here. Here is a laser beam, and you can see the phase. It can go through the standard slit experiment. Everybody would have, or most of the people would have heard. When you pass the laser to multiple slits, and then yet you find if you block one, still there is a appearance of on the other side, and that is because there is an entanglement process. So horizontal and vertical polarization combine, and this is the phase quantum. So sorry, so laser beam based, and we can call it as pulse based and phase. So this is quantum can use any subatomic particle like photon. So it can be photon based, it can be electron based, it can be charge based, it can be uh, atom based, it can be anion based, it can be boson based, any basis, whatever the particles you use, subatomic, and at that level, the it's not like aggregated. So once you aggregate, then it starts behaving like a macro behavior, and these are at the subatomic level where we get the entanglement and indeterminate way of computation through probability. So these are all the particle and wave superposition, and we'll talk about it as we get into more of it. But typically, there are characteristics. We call it as I2CU. I2CU is I is indeterminate. It's a probability of states in transition because we base it on the state basis. State basic states are ket zero and one. We call it as spin up, spin down, ket zero, ket one. Any abstract naming you can use to the qubit. It can be one qubit. If you have multiple qubits, obviously there will be 2 to the power n states. So if you have a 10 qubit, then 2 to the power 10, which will be of the order of 1024 or thousands of states. So different states are involved in this. Higher the number of states, higher the parallel superposition we can apply. Then interference causes decoherence, and we need coherence. So we have to eliminate all this noise, like thermal source of noise can be thermal noise, channel noise, impulse noise, and cross channel and all those. So to eliminate this, it takes a effort, and that is why error correction is important, and fault tolerance we have not achieved still. We are in the intermediate scale quantum era. Uh, so we call it as NISC um, noise integrated. So it's noise based. To eliminate noise, we'll have to do much more, and that is the fault tolerant era we expect to follow now in future. Superposition. Here we have talked about the wave function, wave and particle duality, which we have discussed so many earlier also. Entanglement, again, local and non-local uh, space-time related. So if you are in some local place and then you have some non-local, which it could be moon, which could be sun, how do you do the entanglement? So those kinds of things, which are and imaginary look like, but they are real because of the satellite launches. We can see that happening, and so you can actually uh, control like through telemetry some of these at a distance faster than the speed of light, because that has nothing to do with the speed of light, it has to do with the nature of the entanglement. So then the other operation is unitary, and they are based on the complex conjugate transpose nature of the matrix and vector through which we represent the Hilbert space. Hilbert space is a vector with a complex number, and so it cannot be like a two-dimension. Like if you have imaginary axis and a real axis, and then you have similarly two vectors in two imaginary and real axis, then how do you handle that? It's neither a it's more like a four dimension, not three dimension, not two dimension. How do you handle that? So that is the Hilbert space. So we call it a C2 space, that is complex variable with two dimension. So if you have two qubit, then it is four dimension. If it is three, then it is eight dimension, 2 to the power n. So that is the Hilbert space, which we'll be talking about in later classes. Now, here we show a quantum processing unit QPU, like we have CPU for the um, classical computing, GPU for generally high performance computing, that is the CUDA, that is CPU unified device architecture. Here also you can use, you can call it instead of CUDA, you can CPU unified QPU architecture, quantum architecture, you can say KUKA, but there is no such term. But I'm just saying that you can use that kind of a processing, or you can do native quantum processing. All it boils down to the number of pins available for input and output. And so this is nothing, this is at a um, what you call this is a dilution refrigerator at the Kelvin temperature, millikelvin temperature, where the control lines out of the uh, quantum processing unit is coming out, and these are being managed. And obviously we need multiplexing in all these to reduce the number of pin counts, as usual, like we do in semiconductor. This is superconducting quantum, and this is IBM Condor processor. Courtesy to them for having shared that information. So Quantum and IBM and Google are some of the bigger players in this, and there are other players in the industry. But this needs to grow for us to be able to capitalize this on a bigger scale, and the skill set levels of individuals is what matters, and that is why we have this certification for you to be able to understand and be able to become subject matter expert in a fast-paced way. And here is one of the relativity what we talk about. Because why relativity? Because a lot of people talk about the entropy and use of adiabatic process. When you talk about them, then it is based on the energy level, and energy is nothing but mc square, as per even assuming that you have a rest mass, and if it is relative, that is there is a motion, then you have got half mv square, the potential, the kinetic energy component. So potential and kinetic energy, both components need to be added, and this is the formulation which has come from relativity theory. And there, what happens is the uh, potential and the what you call the static uh, level of the energy is computed together. So example, if you have a photon which is zero mass, electron has a 1.64 into 10 raised to minus 16 or some such number. So electron also you can calculate, but that has got a mass component. But photon, what do you do when there is no mass component? So this is a particle but no mass, or wave with no mass, whatever you call. And then you have got the Planck's constant, h nu, and the c, the light speed of light, 3 into 10 raised to minus 8, and Avogadro's number, or Boltzmann constant, and Planck's constant. These are all related based on the volume and the number of particles, molecules within a given volume. And so this is usable. And the photon also we can compute it h nu, depending on the Planck's constant, and the nu, the frequency of the photon. Like these are in the visible light range, which has in the nanometer and nanometers, or Armstrong as we call it. So that's the level. So the photon energy, depending on the visible range, you can compute the level of the energy of that. So all is based on energy, and so even including our when you measure in terms of the matrix. And matrix, we talk about the diagonal being the trace of the matrix, and the trace and the square root of the sum of the trace when you take. That's what is the representation even in matrix terms. So you will see all of these in future, but important thing to note here is it is based on um, the uncertainty principle, where you can have a whatever parameter of quantum particle, subatomic particle we take, whether it is a photon, electron, charge, and whatever, the corresponding energy level is important, because the ground level to the excited level, how they move, how they are constantly moving. So they carry the energy, but the energy remains constant, and that is why you need the coherent or the adiabatic state. In either case, whether you take a adiabatic process or whether you take a thermal process, we need the energy level to be maintained for coherence, for a computation to be parallelly done, and that's the reason we need to touch this, understand this. Finally, I'll come to the Shannon capacity. I did mention to you the two theorems. One is Shannon's information theory, which deals with the limitation of the channel based on the signal noise, and this is per channel basis, that is single channel. This is only two level. Whereas, suppose if now traditionally we understand that we require for voice around SNR of 1000, which is nothing, 1 in 1000. So basically, our signal should be more powerful than the noise by a ratio of 1000, and that usually expressed in terms of dB and all, and therefore the calculations are in dB. For a 1 megahertz channel example, you can get a 10 megabits per second. For a 2 megahertz, you can get a 20 megahertz. And the same thing, if you have a SNR only 3, then you are going to get lower output. So for a 1 megahertz, you can only get 2 megabits here. For 2, only 4 megabits. So depends on your signal to noise. There is the limitation on the channel. Whereas if you do multi-level, then you can have each channel, like a channel with 5 megahertz, which is the standard 5 megahertz is the wideband capacity of the 5G. So if you take a what you call two level, then you can get a log to the base of 2, which is 1, then 2 into 5. So that is 10 megabits you can get, and which we can see here also we can get, but depends on the signal to noise. Here there is no dependence on signal to noise. So this is the limitation of a given channel only for multi-level. So if you have multi-level, you have 5 megahertz here, then 2 into 5. And because we are talking of 4 level, log to the 4 of to the base 2 will be 2 to the power 2, so it will be 2. So 2 into 2, 4 into 5, 20. So it is a 20 megabits per second. So we should understand the channel capacity, whether it is based on Shannon limitation along with the Nyquist for the multi-layer, which is what we'll be using in the quantum computing. And coming finally to the glossary, some of the terms, IEEE has got the glossary, which was provided to by IBM to standardize, and it's still in the evaluation process. But most of them people stick to the IBM glossary for terminology. And like example, I can give you, if I ask what is ansatz, ansatz is nothing, a approach or attempt or assumption about certain unknown function. So example, if I know there is a oracle, oracle is a black box. So if I say, I have a oracle for quantum, if what it means is I have a black box, and this is an assumption I am making. So it's an answer that we are making about oracle. So this is nothing but quantum gates. So there are many terms like this which are different from normal digital circuits and all that. One example is another is clocks, that circuit layer operation per second. This is clocks is for performance of the depth and width of the circuits in quantum which we use. So these are various terminology. All is you have the link to it. You can go through this, understand the difference, because terminology is what matter at the end to be able to grasp what we are talking about quantum. And so early you refer to glossary, the better, and that's only part of the your exercise. So what we have covered salient points is that quantum computing is based on manipulating the subatomic particle that exhibit characteristics which have exponential power to do the operation. So they call it n qubit is 2 to the power n, compared to classical, which is n qubit. So you have 8 qubit, 16 qubit, 32 qubit. So you have only that. And you don't really see classical computer going one above 128 bit, because most of the operation we can do within those using the floating point arithmetic and etc. So but in this case of it's a parallel operation, and there is a quantum memory, which is nothing but the atom itself is the, or electron itself is the memory. And so you maintain the electron in certain states for certain time and try finish the computation faster. Then building on a quantum computing is non-trivial. Of course, it is non-trivial because you have to you operate them at low noise temperature, especially the superconducting quantum. Same with adiabatic also. They also need to be at the low temperature using the helium, nitrogen, whatever gases they use to maintain the adiabatic process. So the potential of this is very good because it can solve non-polynomial hard problems, and like example search algorithm growers, prime number factorizing like Shannon's, QFT, IQFT, that is the quantum Fourier transform, inverse quantum Fourier transform, etc. So we'll see, talk about it as we go to the next future lectures. But control circuit implementation is very important, and quantum logic, which is run at millikelvin, is very important for the quantum operation or subatomic particle. And we have a drive here shown to you, which you can use it for, available for share for, with all the information that we have been. If you have any questions, you can send it to pramchan@eotf.in. I'll answer you. And this is the first session, and I think I will end the recording on this session to be able to put it out. And we have other sessions. You can look at session 2 and 3 as we publish them. You can go through them. We conduct the classes every Saturday. We have finished around, so next Saturday we'll have, well, coming Saturday, I mean. So that will be our fourth session. Thank you. And we pre-record or post-record whichever is possible, and then you will have all those available through the SE Silicon Valley Quantum Meetup as well as through the EOTF YouTube channels. With that, I will stop, and we will have Q&A. We will be sending those who are interested in certification will have to answer the questions to be able to qualify for the certification, and watch the videos, and then take notes. If you're present, then you can get Q&As also answered, and that's the process we are going to take. And we are targeting that it is not like 1 day 2 day affair. We want you to this to sink in. So I think we should be able to complete by December. By Christmas we will be awarding the certificate based on the classes you have gone through, either the recordings and based on your answering of the quizzes that we have been providing. And those are the uh, ways to evaluate, and we look forward to your participation. Thanks very much. With that, I will close the call for today. Thank you.